Good morning. In the last two classes, we have discussed the idea of spin and we have also discussed some of the properties of commuting bracket. So now we are in a position to discuss the spin of a Dirac particle. The electron spin carries no energy in itself, so it can be observed only through its coupling with the orbital motion of the electron. Now let us consider an electron in an atom. Then we can define an orbital angular momentum, which is expected to be a conserved quantity. If its orbital angular momentum is represented by the term L, then it is expected to be a constant of motion. But in quantum mechanics, a dynamical variable that is conserved should commute with the Hamiltonian. And according to the Heisenberg picture, if a particular operator AH is conserved, then the commuting bracket AH should be 0 and its value is given by IH cross dAh by dt. So here we are considering the orbital angular momentum L, since it is expected to be a conserved quantity. Using the Heisenberg picture, we can write the commuting bracket L EH, which is equal to IH cross dL by dt should be equal to 0. Since the orbital angular momentum is conserved, this particular commuting bracket is 0. So the value of IH cross dL by dt equal to 0. It means L is a constant of motion. So now we can check the value of IH cross dL by dt. So we are considering a three-dimensional problem. Here the total Hamiltonian is given by, according to Dirac, it is H equal to C into alpha dot P, that is C alpha x Px, C alpha y Py plus C alpha z Pz plus beta M.Sc square. And the angular momentum L is given as L is equal to R cross P. So if we are considering the x component, the term will be Lx H equal to IH cross dLx by dt. So its value is expected to be 0. Now we can calculate the value of this particular commuting bracket. The x component of orbital angular momentum is given by L is R cross P. So we can calculate it like IJK Ax y z Px Py Pz. So its x component will be ypz minus zpy. So the value of the commuting bracket Lx H is ypz minus zpy, and the H component is C alpha x Px, C alpha y Py plus C alpha z Pz plus beta M.Sc square. Okay, now we can calculate this particular commuting bracket. In the last class, we have discussed how to calculate this commuting bracket, and we have mentioned some of the properties. And the position and momentum operators commute with the alpha and beta matrices. So our commuting bracket R alpha or commuting bracket R beta or the commuting bracket P alpha or the commuting bracket P beta. The values of all these commuting brackets are 0. And also the position operators and the momentum operators commuting among themselves. So the commuting bracket Qj Qk equal to commuting bracket Pj Pk equal to 0. So we can write down the value of this particular commuting bracket as using these relations. We can neglect some of the terms and we can consider only those terms which have some probability to exist. When you consider the first term, that is the combination of ypz with alpha x Px, alpha y Py, alpha z Pz and beta M.Sc square, only the term which contain y and py should exist, and all other commuting bracket will be 0. So we can write it as y Pz comma C alpha y Py. Similarly, when you consider the second term, the Z commutes with the Pz. So we can write only the commuting bracket Z Py comma C alpha Z Pz. Now you can apply the distributivity property. I am not going to write down all the terms. while writing the terms, the first term ypz, here the y commutes with the py, so you have to take the c alpha y to left side, that is c alpha y, then you will get py. The second term will be 0, that is ypz c alpha y into py, that will be 0. Similarly here you have to this z commutes with pz, so by applying the distributivity property, you have to take the c alpha z to left side, then you will get c alpha z into z py comma pz. There will be one more time, that is you have to take this pz to right side, then it will be coming bracket z py c alpha z into pz, and its value is 0. So it is equal to c alpha y into, you can again apply the distributivity property. So you can take this pz to right side, so it will be y py into pz. When you take this y to left side, the term will be 0. Similarly from here, when you take this py to right side, the value is c alpha z pz into py. When you take this z to left side, the commuting bracket py pz is 0, so its value will be 0. So you can write it as c alpha y into commuting bracket y py is ih cross, so you can write it as ih cross pz minus c alpha z, its value is ih cross, so ih cross py. So you can take an ich cross common, so what we will get is the commuting bracket lx h equal to ih cross d lx by dt, its value is ich cross alpha y pz minus alpha z py. Let it be equation number 1. So on physical grounds, we are expecting the angular momentum to be constant dlx, so this particular commuting bracket should be 0, but we are getting a non-zero value here. That is, the x component of the angular momentum is not conserved, it changes with time. Similarly, we can calculate the value of the commuting bracket lyh and lzh. So from this calculation, what we are observing is that the value of lx, ly and lz are not constant of motion. That is, the angular momentum L is not a constant of motion. However, on physical grounds, we expect the system to have a total angular momentum which is a constant of motion. How can we solve this problem? The only way is we can expect one more contribution to the angular momentum such that the commutator of its x component with the h should be the negative of this quantity. That is, we should get some minus ich cross into alpha y pz minus alpha z py. Then when you take the sum of these x components, then the right hand side will be 0, such that it will be conserved, and then you can interpret that particular sum as the total angular momentum. Now it can be easily shown that the desired additional contribution comes from the operator h cross sigma dash, where sigma dash equal to sigma 0 0 sigma, that is here the sigma is the Pauli's spin matrices. So now we can calculate the value of ih cross d sigma x dash by dt. Its value will be equal to sigma x dash into sigma x dash h, and the value of Hamiltonian is sigma x dash c alpha x px plus c alpha y py plus c alpha z pz plus beta M.Sc square. Now you have to calculate this particular commuting bracket. Now there is no need to calculate the commuting bracket sigma x px or sigma x dash py or sigma x dash pz, because this particular matrix contains only terms 1 or I, like that. There is no terms including x, y or z. So when you calculate the value of this particular commuting bracket, that is sigma x dash px or sigma x dash py or sigma x dash pz, its value will be 0. Now we can calculate the value of the commuting bracket sigma x dash beta. So its value is sigma x 0 0 sigma x 0 sigma x 0 minus 0 sigma x 0 sigma x 0 0 sigma x, when you calculate the first product, you will get the value of sigma x square is 1. So you will get 0, 1, 1, 0 minus 0, 1, 1, 0. Its value is 0. So the sigma x dot commutes with alpha x. Now we can calculate the commuting bracket sigma x dash alpha y. The value of the matrix alpha y is 0 sigma y 0. So when you calculate the first product, there will be one time sigma x sigma y, its value is I sigma z. When calculating the second product, there will be one time, there will be terms like sigma y sigma x, its value is minus I sigma z. So you will get the first product is 0 I sigma z, I sigma z 0 minus 0 minus I sigma z minus I sigma z 0. When we subtract these two matrices, you will get 0 2 I sigma z 2 I sigma z 0, and you can take 2I outside, so you will get 2I into 0 sigma z 0, and it is the matrix alpha z. So you will get 2I alpha z. So the value of the commuting bracket sigma x dash alpha y is 2I alpha z. Similarly, you can calculate the value of sigma x dash alpha z. While calculating that particular product, the particular commuting bracket, here the matrix will be 0 sigma z 0. So in the product there will be terms of sigma x sigma z in the first term, but the value of sigma x sigma z is minus I sigma y. So when you calculate this particular commuting bracket, what you will get is minus 2I alpha y. Okay, you can easily calculate this particular commuting value of this particular commuting bracket, and its value will be minus 2I alpha y. So now we can write down the value of IH across d sigma x dash by dt. Its value is d sigma x dash commutes with alpha x and commutes with the px. So its term, all the terms will be 0. While considering the second term, the sigma x dash commutes with the py, but it does not commutes with the alpha y. So you have to calculate the term sigma x dash c alpha y py. Similarly, in the third term, you have to calculate the value of sigma x dash c alpha z pz. The sigma x dash commutes with the beta, so its value will be 0. Now we can calculate this particular commuting bracket. So now you can use the distributivity property to split this particular commuting bracket. The only existing element will be sigma x dash alpha y into cpy. When you take the c sigma y to the left side, the sigma x dash py commutes, so its value will be 0. Similarly, for the second one, you have to take this c pz to right side, so you will get sigma x dash alpha z into c pz. When you take the c alpha z to left side, the term will be 0. Now we can substitute the value of sigma x dash alpha y. Its value is 2I alpha z. Here the value is 2 minus 2I alpha y. So its value is 2IC alpha z py minus 2IC alpha y pz. So you can take on minus 2IC common. So you can write minus 2IC into alpha y pz minus alpha z py. So we get the relation IH across d sigma x dash by dt equal to minus 2IC alpha y pz minus alpha z py. And for the value of IH across dx by dt was ICH across alpha y pz minus alpha z py. Now we are looking for a conserved quantity, and for getting a conserved quantity, when you take the sum of these two equations, the right hand side should be 0. For that, you have to modify this particular equation. Here the term is ICH across, here on 2 is there, so you have to divide the whole equation by 2, and also you have to multiply the equation with the H across. So what you will get? you will get IH cross d by dt into you have multiplied with an H cross and divided by a 2. So H cross by 2 sigma x star, the right side will become minus IC H cross. So now if you take the sum of these two equations, the right hand side will be 0. So when you add these two equations, you will get d by dt of Lx plus H cross by 2 sigma x dash equal to 0. The time derivative of this quantity is 0, which means Lx plus H cross by 2 sigma x dash is a constant of motion. And similarly, expressions are all good for the y component and z components. Therefore, the quantity L plus H cross by 2 sigma dash commutes with the Hamiltonian and can be taken as the total angular momentum. Now, from the structure of the sigma dash matrices, we can write sigma x dot square equal to sigma y dot square equal to sigma z dot square equal to 1, and this gives the eigenvalues of half h cross sigma dash as either half h cross or minus half h cross. Therefore, S equal to half h cross sigma dash equal to half h cross sigma 0 0 sigma can be interpreted as the spin angular momentum of the electron. Thus, the concept of spin has evolved automatically from Dirac's Hamiltonian. So now we can conclude the total angular momentum of an orbiting electron is 0, but if you consider only the contribution from the orbital angular momentum, the quantity is not conserved. So you have to consider one more contribution, the spin angular momentum, such that the sum of this orbital angular momentum and the spin angular momentum is a conserved quantity, and the sum of this orbital angular momentum and the spin angular momentum is taken as the total angular momentum. And we have seen that the value of spin of an electron is h cross by 2. It can take two values, either h cross by 2 or minus h cross by 2. That is why we are taking these values are either up or down. Okay, thank you.